it's so many people here. Okay, so let me introduce our speaker, Rohan McLure. So Rohan is a first-year grad at IBM, mostly hacking on the Linux kernel. The Linux kernel strives to be backward compatible for user space. Today, Rohan will talk about the time that he accidentally broke that promise. Please welcome Rohan.
Two apologies before I begin. I was awake in Canberra at 4 a.m. this morning, and so I may be a bit loopy. The other apology is for presenting a talk about the Linux kernel from an Apple laptop, but thankfully for your sake, I save you the secondhand stress of watching me ex-randa. So I'd like to begin today with an acknowledgement of country. I begin today by acknowledging the Wurundjeri Woi Wurrung people of the Kulin Nation, traditional custodians of the land on which we gather today, and I pay my respects to their elders past and present. I extend that respect to Aboriginal and Torres Strait Islander peoples here today. Hi, my name is Rohan. Thanks for coming to my talk. So for the last year and a bit, I've been hacking on the kernel as well as OpenSSL, and just in my first patch series, I managed to really max out on the number of people I could irritate. I've made my first patch series, and a month after it's upstreamed, I get this sort of feedback. This breaks PowerPC 32-bit. Probably breaks every syscall with a 64-bit argument. All right, great. So what's the damage exactly? Well, a bit of an introduction to the kernel. Perhaps it needs no introduction, but I'll give a brief one. At 1,000 feet, there sits a sort of dichotomy between kernel space, which is privileged, and user space, which is basically unprivileged, and essentially two security rings in this sort of monolithic kernel. And so user space relies heavily on the kernel then for its process management, for its file system access, for just general access to resources, etc. And so with that comes a number of software contracts. And so if you were, let's say, trying to break all of user space, that is all unprivileged programs on your system, what might you do? Well, you might actually violate these contracts. For those of us unfamiliar with the idea of a software contract, essentially, if you've programmed it all, you've used some sort of API. An API stands for an application programming interface. And critically, I'm going to draw on this distinction later. It's a sort of contract on source code. It's usually not difficult to consume someone else's library when you have tooling which supports you doing so. That is, there's a common ABI, which I'll get to in a moment, so that you can call library code, provided the parameters, which the documentation, if there is documentation, or examples, if there are examples, or code, if there is code. You can usually call that library subject to its specification, and an API implies that that library is intended to be stable to some extent, and it has exported functions. And you can call it without risk of personal injury at some rate. But contrast that, however, to an ABI, an application binary interface. What keeps programs which were compiled yesterday or just as easily 20 years ago, what keeps them running on modern systems? Well, that's an application binary interface. And these are extremely prescriptive. This covers stuff like calling convention, as well as the focus of this talk is on the syscall interface. So I'll get to that in a moment. But ABI is extremely prescriptive, is what's worth knowing. It's down to exact register allocation and stack layout. With an API, you can call your library, and as much as your toolchain has support for that, perhaps a foreign function interface, with ABI, it prescribes exactly how binaries look and how the kernel must respond. So there are actually a number of ABIs. It's not always just user space to kernel. Usually, when it comes to ABI, the base, right, is what's your object format which you're compiling to. If you're compiling code for modern Linux, that's almost always ELF, the executable and linkable format. On top of ELF, you get further further specifications which come from your choice of architecture, the machine which you're compiling for. Architecture is, sorry, ABI, by the way, is not ISA, instruction set. ABI defines things like calling convention, for example. And then even operating system can further constrain ABI, that is how libraries and their consumers operate. But the particular level of ABI we're going to talk about is what's called the kernel to user space ABI. And that one is stable, intended to be stable. There's another ABI in the kernel, which is the kernel to modules ABI, but that's not the one I broke. So we're going to talk about this one. Yeah. So about the Linux kernel to user space ABI, this particular bit of the ABI is about the sort of tools which arbitrary binaries on a Linux system should be able to rely upon existing on their system. So they include things like the VDSO. That's the virtual dynamic shared object. It's a library which is always mapped into process memory whenever you load any sort of ELF file. As well as that, there's the syscall interface. I'm going to talk more about those in a moment. The VDSO actually exists to circumvent some of the performance ramifications of syscalls, which almost always imply a sort of context switch. And so system calls have been opted out so that your libc can choose to call things via the VDSO if appropriate. As well as that, there are also file systems. So Linux participates in a sort of Unix file-based ideology, and so access to your sysfs, procfs, and the little-known config.fs are also deemed to be ABI. This talk is going to focus on syscalls, however. So what actually is a syscall? I think at 1,000 feet, again, the way I describe it is a sort of pseudo function call. That is, when it comes to control flow, the same pattern exists. So your code will eventually yield when you initiate a syscall, when the syscall should terminate, hopefully, and then execution should be resumed at your calling process. And so Linux is a bit interesting. I'll talk more about this in a moment, but this is the sort of code which the kernel is expected to support, right? So I don't know how familiar you are with power assembly. I'll walk this through with you. So as per the calling convention, we're going to specify in R0 what sort of syscall we want to do. Clearly, we want to do an exit. First parameter is 0, exit with status 0, syscall. We have 2 syscall instructions on power. Your libc will choose the most recent one. In short, this syscall instruction is a way for unprivileged code to cause the kernel to facilitate some sort of critical function call. And so nearly always, the way this is implemented in hardware is by means of an interrupt. This syscall is a synchronous interrupt. In general, your interrupt hardware works for events which can fire at any time. But this is an interrupt instigated by code, and that interrupt handler is expected to fulfill the contract of whatever syscall you just called. A really critical syscall is fork, for example, and this is just to motivate how privileged, how much reflection on program data these syscalls end up invoking. So this is a process and threading control syscall, and it's being abstracted out by libc, so I can just call the fork function. And so fork has to look at the entirety of your process state, and what it does is it duplicates that thread. That is, it duplicates its memory mappings, and it keeps the same instruction pointer in the resultant thread. And so when the threads wake up, they both resume execution after the call site, and you'll notice that we take a return value, PID. That's our process ID. It's 0 if we're Frankenstein's monster. It's the name of Frankenstein's monster otherwise. And you branch on that condition. Figure out whether am I the child thread or am I the parent. And so syscalls, yeah, they're a sort of function. Or rather, they have a function-like kind of interface. But interestingly, the function calling ABI and elf is not actually, doesn't 100% line up with syscall calling conventions. But clearly, this is a very privileged operation, which, well, a few more bits of aside before we cut to the chase. So Linux is a bit interesting. Above, you can correct me on the nuance of this later, but above other free and open source operating systems, Linux has a particularly high commitment to keep a stable syscall interface. That's because you don't usually, as a programmer, invoke syscalls directly. You might use libc, and Linux doesn't in principle prefer a canonical libc implementation, and so the syscall interface is deemed to be authoritative. Certainly, your proprietary operating systems avoid syscalls at all for user space. So there's libsystem on macOS. Syscall interface is not deemed to be stable. And then you have nt.dll on Windows. But yeah, Linux has this kind of extreme attention to detail when it comes to ABI. It's best summed up by this one particular Linus quote, which is of course in all caps. We do not break user space. And so that's what I did. All right, well, all right, so we have our interrupt code, and because the kernel is essentially just this stitched together, big old massive ELF binary stitched together by link scripts, we have these symbols in here for the actual body of a syscall. Our interrupt code is going to call this body. The interrupts are handled by kernel. And so they used to have this sort of calling convention. However, to give a little bit more freedom to how we write our interrupt code, we decided to use some ugly and horrible macros to change the calling convention to look like this. You don't need to know what a ptregs is. It comes from ptrace. I can't tell you any more of the etymology. Try again. It's in actual fact just a structure which represents the registers of the caller of this syscall, because it's an interrupt, right? So there's an entirely new context between user space code, which called us, and kernel code. We keep that context, and we're expected to save and restore it accordingly, hence a context switch. And so we want to change that calling convention, steer cleared for a bit of motivation on why we do that exactly. But the kind of crown jewels is I've been inducted onto the hardening team, and so we decided we'd do a hardening. And part of that included we wanted to essentially sanitize whatever continuity there is between user space code and kernel code. And so whenever user space can directly or directly enough invoke an interrupt of any sort, we don't want the architected register state of that user code in any way influencing the speculative runtime behavior of the kernel. And so what do? We have to save even more registers for this mitigation. We sanitize those registers. We set them to 0. And then we restore those registers before we return. And if it's not obvious to you that there's an exploit kind of in the waiting here, then that's fine. It wasn't obvious to me either. But let's just sort of dive into the activity of kernel hardening, right? So there's been a sort of seismic shift in the world of security research with Spectre and Meltdown, which is to say that user space may not be able to leak secrets from the kernel directly, but it might be able to do so in an implied fashion through timing attacks. And these timing attacks become increasingly available with an awareness of the reality, which is that microarchitectures are necessarily speculative on superscalar processors. And so what we're doing is hardening measures, right? We're just trying to produce isolation between user code and kernel code. And so I can't actually guarantee you that I've foreseen exploits per se, but it's a bit tedious to just chase after exploits when they become discovered, right? You'd rather harden the kernel against the prospect of people gluing together info leaks and gadgets and one day creating an exploit. And so a bit of a red flag which alerts you to the fact that this might need hardening is that there is shared architected state. That is, the registers of the calling code are in fact retained, although cleared pretty quickly by kernel code. If, by the way, if there's an architectural bug, we've got bigger problems. So we're on the microarchitectural level here. Okay, so a quick aside as to how syscall wrappers are implemented in the kernel. I promise to not show you too much code. So there's this syscall define for macro, and so this kind of creates the signature, the prototype. What's it called in C? The prototype for the fallocate, fallocate syscall handler, and it's going to prepend this sys underscore prefix to the beginning because no one should be directly calling it by name. And so if you're going to create your own syscall, if you're mucking about with the kernel, you'll define the syscall like such, and then you'll add a number in a table to say when R0 is this number, in kernel, please call this syscall for me. What we're going to do is, in order to get our new calling convention for these syscall handlers, like any good C programmer would, we're going to write an ugly macro. And that ugly macro better implement the calling convention perfectly with no bugs ever for our syscall handler. And so clearly this is where my bug came from. As a bit of an aside, so I work on power systems, Linux on power. We have our own subsystem, Arch PowerPC, and there are about 12 million lines of code in the kernel, not including modules, not including user space libraries, tests, etc. About 4 million of those lines is architecture specific, and about 500,000 of those lines sit in Arch PowerPC. So it's a big subsystem. Why is it so big? Well, you could hint to a few things, I suppose. For comparison, ARM has spun off its 32-bit and 64-bit subsystems. And so we're like x86 in that respect. They're both under a common subdirectory. But unlike x86, we're by endian. So you end up with this kind of horrible matrix of kind of platforms running on Arch PowerPC. And sometimes the same code services all 4 of these platforms. ABIs are fiddly enough, and so with 4 sub-architectures of sorts, yeah, necessarily there are going to be at least 4 ABIs I need to implement. And ABIs, right, are meant to be implemented by toolchains, because they're fiddly, and not by crappy macros. So how did I do in my patch series, my first patch series on the kernel? Well, as a little babby kernel developer, I had to touch a lot of untouched legacy code. And I started off with 6 patches in my first revision. And if you don't know, in the kernel, we do our communication over email, which is insane to me. And once you send off saying, hi, I'm a young and not yet cynical kernel developer, and I would like to modernize your stuff, you get a laundry list, right, of things which you should fix. And so by the time I submitted part of my patches, it was revision 6, and I had 25 patches on the list, which was ridiculous. Most of them got into kernel 6.1, but the actual hardening component got into 6.2, because again, if you went to Russell's talk, everyone will complain if you make your CPUs like 2% slower. Yeah, like where I really hit a wall is with these 32-bit calling conventions. I really did work hard to make these work. Did I miss a slide? No. All right, I really did work hard to make these work, but there are just some cursed special cases. So here's a relatively normal syscall, sys fadvise 64. Where does the 64 come from? Well, this loft t, you know if you know, that's always 64-bit, irrespective of what toolchain you're using. I think that's a POSIX thing. Yeah, well, some architectures actually want you to implement this one too. This is where it gets a bit cursed. You notice that the advice parameter actually changes its position. This is probably the most attention you've ever paid to this fact. But the reason why it does that is because there's a sort of soft rule of no more than 6 parameters to syscalls, because calling conventions on all these architectures do register-bound syscalls. Most of them architectures do register-bound syscalls for the first 6 at least, and so that's kind of common. See, 32-bit machines still need to be able to send these two 64-bit params. That's the lofties I'm pointing to. How do you send a 64-bit parameter with 32-bit arguments, registers? Well, you obviously split it in 2, and so that comes to 6. And why did we have to move advice to the back? Well, it's because these architectures in their function calling conventions specify that these register pairs, which unite to become single 64-bit values, these register pairs better be odd even in their indexing. All right, so yeah, so some 32-bit args kind of expect the syscall handlers to look a bit like that. And then the order of LO and HI in each case is going to be dependent on endianness. Yeah, well, all of these are implemented not in generic code. They're implemented in PowerPC, and they were last edited in 2005. So I had to clean up a whole bunch of them. They weren't even using the macro I showed earlier. So yeah, a lot of fix-up. I won't bore you with the details. And then there was this little gem. All right, well, so it turns out, because this is a syscall, right, and we don't break user space, this was ABI for a while. This was I couldn't change this without much arguing. So in short, there was this crazy like PowerPC 32-bit only syscall where it would check whether the first parameter is a pointer or not by seeing, is it bigger than a prohibitively large number of file descriptors? And if so, it would arbitrarily decide, use these old semantics, if not, use these new ones. And that's nuts. So after quite a bit of arguing and then resuscitating all conversations on the mailing list and saying, no, look, we really were going in this direction, just people didn't have time. We should just replace this with something sensible. And so I finally cut out this thing and replaced it with sysselect. Besides, the way I'd set things up, you couldn't reliably recurse syscall handlers, so this kind of had to go anyway. Details. All right, so how did we do with performance, right? So we're having to save more registers in that we hope to sanitize all of the user's registers and then eventually restore them. And so saving to the stack, restoring from the stack, it's going to be hella slow, right? Oh, sorry. Sanitizing more registers. Clearly that's more work on every context switch. And it turns out I made things faster. I made context switches faster, accidentally. And so I've hence been summarily removed from the hardening team, because that goes against our secondary goal, primary goal, just making context switches slower. It turns out that I made them 14% faster. You can ask me in questions how. Even with the mitigation kicked in, context switches are still 5.6% faster, so that's nice. All right, so you didn't come here to hear me waffle about syscalls. You came to see me break things. So, right, well, this is the feedback I got. And after a little bit of a frantic slurry of trying to figure out what was going wrong, this is what I figured out my macro was doing. If you don't like debugging macros, then good. So my macro spits out these 3 symbols, just in various stages of trying to unpack this args parameter. And you don't need to see all of them, because right here you can probably see the problem. If you're facilitating a 32-bit calling convention, by the way, you should be able to run 32-bit programs on a 64-bit machine. There needs to be compatibility. If you're running 32-bit, my macro, basically, it cuts out here. It sees that this is a 4 arity syscall, and so it only emits the first 4 registers. So it breaks calling convention. And I knew about this, right? I just didn't know that there were any syscalls left in the kernel after I had done all my work that were expected to run on both 32 and 64. And so the rest of this is all a wash. But yeah, that's some cursed macro. And yeah, just to kind of spell it out a little bit further, we only pass in 4 registers. The last 2, R5 and R6, should be parts of the offset parameter, but instead they're interpreted as a random bit of offset and a random bit of len. And so this is what the macro should spit out, but it doesn't, which is not good. And yeah, so the exact part of offset and len, which are represented by each of R5 and R6, basically that's sort of random, but not quite random. That's determined by our endianness, which brings us to the next bug I wrote. And there's nothing really deep here, but I thought I would give back to the community, and I would define this compat arg u64 dual macro. There's a subsystem in the kernel you may be interested to know called asm generic, and asm stands for assembly, and it's like generic assembly. Essentially, it's bits of macros which all architectures could benefit from there being common code, and people override their own macros. And so I overrode these macros so that everyone can have a compatibility version of fallocate, everyone who chooses to, and that compat arg u64 dual, that's going to split offset into a low portion and a high portion. And then the order of those low portion and high portion is going to be determined by endianness. Well, I got that wrong. I got that flipped around the other side. And my patch series went through 6 revisions, and somehow no one caught that. So I really was just hitting high scores here. And I had, in fact, bricked RISC-V 32-bit and PowerPC 32-bit at this stage. A prominent member of the kernel community made a comment about this. See, the blunders which I'd made, right, they were great in nature, but not great enough to topple 2-hall architectures, because no one's really running these upstream kernels. But a certain prominent member of the community decided to chime in, saying, is it just me, or did this break every architecture? Did this grad just manage to destroy everything? And people just didn't scream because 32-bit code has become so rare. Thankfully, it was just RISC-V and PowerPC, so no one noticed. But but every cloud has a silver lining, and I got my first shout out from Linus. So by means of conclusion, essentially, yeah, I'm a first-year grad. I got to work on the Linux kernel, which supports the vast majority of web servers, which is kind of amazing. And it's just kind of amazing how easily someone can throw their hat into the ring and work on essentially just infrastructure, which everyone depends upon. And essentially, my ability to contribute as much as I have is really owed greatly to the rigorous reviewing. This is not a joke, by the way. These tests, the people really did boot kernels on 32-bit. And it turns out they didn't actually corrupt enough to not boot, which is delightful. So it was one of those kind of wicked problems, but they certainly were corrupting. And really, anyway, my ability to get this far is very much, I'm thankful for the testers, the reviewers, and the maintainers who makes this possible. Essentially, what I want to say is that persistence seems to be a sort of key skill for kernel developers, and that if you're someone who enjoys low-level programming, and you're willing to go through a mailing list, to go through multiple lines of reviews, you really can actually contribute to some pretty significant software projects. And there's always work, it seems, manually manipulating registers. But if you have this sort of meticulous attention to detail, yeah, you can contribute on most things. So I hope in hearing this talk, this encourages you to contribute to the projects which interest you. And I hope that your first patch series is not quite this cursed. Any questions? Yep.
So how did you speed up context switches?
Yeah. Yep, good one. So should I show some kernel code for this one? That might take a little while. Go ahead. Okay. I closed my editor. Okay. Well, in short, there's been a number of reforms to replace what is a whole bunch of assembly. So we use GNU assembler to write our interrupt handlers at the exact region in virtual memory where interrupt handlers are expected. And then we just have we have a number of trampolines which eventually call into C code. And then the rest of everything is performed in C code. In short, when I changed calling conventions, I know what I'll do. I'll just show this slide. Yeah, so when I changed calling conventions for these syscall handlers, I was also able to change the calling convention of some of these C functions, which facilitate these interrupts. And that might not sound like a lot, but in principle, these syscall handlers can take up to 6 arguments. So that's 6 of the scratch registers consumed. And so what I did is I just freed up register allocation, in short. So it decreased the total stack utilization. And it turns out that, yeah, I got more than 10% speed up, which is kind of phenomenal there, actually. Not at all what I expected. Yeah, there's another part to that, but I've forgotten. Any other questions? Hey.
Sort of a two-parter. Like, how much background did you have, like, in kernel development or like looking at this kind of low-level development before you got stuck into this work? And secondly, why was RISC-V impacted along with PowerPC?
Good one. Okay. Yes. So what background did I have? I primarily got into low-level programming actually by just writing simulations. I've touched a bit of Fortran, but thankfully mostly in C. So yeah, just working with low-level libraries like MPI and OpenMP and whatnot. Yeah, and I just discovered that I just like tuning, optimizing things, which is cool. Yeah. And then later on, I got into kernel dev. I took a class at uni that kind of interested me to read a whole bunch of kernel code, but didn't have any projects immediately which I necessarily wanted to write in the kernel. And so, yeah, I really did come in blind at some rate in terms of the context of what I was looking at. And actually, this was a really good first task working on syscall handlers, in that essentially, so the syscall interface is, I imagine, probably the largest user to core kernel interface, and so the user code needs to request resources of all sorts, and so it should eventually touch all subsystems in the core kernel. And so yeah, I got to read quite a bit of code that way, so it was a good induction. And then your second question, how did I break RISC-V as well? Let's get back to that slide because I don't think I explained it super well. In short, I implemented this compat arg u64 dual macro that was already implemented and being consumed by RISC-V, and I opted in PowerPC to using it so we could remove some of our own custom syscall handlers, which were basically the same. But critically, I exchanged their working version of that macro for one which broke. Yeah, I misplaced a if def big endian. Turns out not all architectures have a if-def little endian, which is weird. More architectures are likely to have a macro called defined config big endian than config little endian, which is weird because more architectures, I imagine, are little endian than, and whatever. Pardon? Yes, indeed. Well, I suppose if little endian's the default, then anyway, whatever. But in short, I realized this, that, oh, if I have if config little endian, I'm going to break a whole bunch of architectures. And so I decided, let's not use that. So I decided to use if in def big endian, except I missed the n, missed out on the n. And so did my reviewers, apparently, so can't have been that important. Yeah. Any more questions?
So I have a fully non-technical question. As a
Cool.
newcomer to the Linux community, what, if anything, do you think should be different about the Linux development culture to get more people like yourselves who are newcomers to involved and working upstream?
Yeah, I would say that, I mean, the grads of today are natives, right, in at very least GitHub. I think I'm only touching on concerns which are, I think, pretty broadly felt even within the kernel community, who've solidified their workflows now for some years. But yeah, I think the key thing is the way people contribute. New grads will be more familiar, of course, with merge requests or pull requests, or if you're on GitHub, and the way CI works. Kernel CI, there's a talk happening at this conference about it. Kernel CI has quite a long history. There are some really good examples of it. With for example, the 0-day CI, which Intel does, has been very helpful. But ultimately, we built up this matrix, right, of the sub-architectures present on PowerPC C. That's really the tip of the iceberg, because there are any number of modules and configs of any sort. So essentially, the matrix of things which you might want to test become enormous. There are some very good talks from previous LCAs on the state of testing. But yeah, fundamentally it's testing and how do you contribute. Setting up your mail client to be able to contribute is kind of non-trivial. And so just decreasing that barrier to entry. I'd say barrier to entry.